Integer divisibility. Here we have the multiplication table for 3, or at least part of it, as it is infinitely large. Often when we write down such a table, we only consider the positive numbers in it, these ones. But here I'm also including 0, which is a member of the table, and these negative numbers, which are members of the table. The integers in the table are called multiples of 3 because every number in the table can be made by multiplying 3 by some other integer. So, for example, we can make 12, which is a member of the table, by multiplying 3 by 4. And so, for example, minus 15 is in the table because minus 15 is minus 5 times 3. 0 is in the table because 0 is 0 times 3. 6 is in the table because 6 is 2 times 3. And 12 is in the table because 12 is 4 times 3. And the same holds for any other integer in that table. Now, we've called the numbers in the table multiples of 3, but we can also say that 3 is a factor of the integers in the table. When we use the term factor, we're usually thinking about decomposing numbers in the table into 3 times some other integer. So 6 decomposes into 2 times 3. 12 decomposes into 4 times 3. Minus 15 decomposes into minus 5 times 3. 0 decomposes into 0 times 3. We can also think about the table from the point of view of division. An integer is in the table if we can divide it by 3 exactly, i.e. if on division by 3 we produce an integer and we leave no remainder. So minus 18, minus 15, 0, and 6 are all in the table because they all divide by 3 exactly. They respectively produce minus 6 and no remainder, minus 5 and no remainder, 0 and no remainder, and 2 and no remainder. We say that the integers in the table are divisible by 3, or that 3 is a divisor of the integers. And we can now define integer divisibility. Suppose that a is an integer and b is an integer, then a divides b if we can find some integer k such that b equals k times a. And we should note that even though we're talking about integer divisibility, we define it in terms of multiplication, which you might consider to be slightly odd. And if a divides b, then we can use the following notation, a followed by this bar b, to denote that, and we read that simply as a divides b. And now we'll look at some examples to clarify that definition. 3 divides 12, since we can make 12 from 3 by multiplication by another integer. 12 is 4 times 3. Minus 3 divides 15, since 15 equals minus 5 times minus 3. We can make 15 from minus 3 by multiplication by minus 5. And this example also makes the point that a divisor can be negative. Now we know that for any integer a, 0 times a is 0. And that tells us that a divides 0 for any integer a. Any integer a at all divides 0. Now we can also show that 1 divides any integer. That's because we can make any integer a by taking 1 and multiplying it by a. That is true for any integer a. So for any integer a, 1 divides a. In addition, any integer divides itself. That's because if we start with any integer a, we can multiply it by 1 to produce a. So for any integer a divides a. Now note that we can't produce 8 by taking 5 and multiplying it by some other integer, because 5 times 1 is 5, which is less than 8. 5 times 2 is 10, which is greater than 8. And there is no integer between 1 and 2 that we could multiply 5 by to produce 8. So we say that 8 is not divisible by 5, or 5 does not divide 8, and we use this notation to indicate that fact, a vertical line with a bar through it. Now we have to be a little careful with 0 when thinking about divisibility. It is the case that 0 divides 0 according to our definition, since we can make 0 by taking 0 and multiplying it by 0. So 0 divides 0, since 0 equals 0 times 0. However, that does not mean, and this is a very important point, that 0 divided by 0 equals 0. You cannot write that fact down. It is false. We can also note that 0 divides no other integer at all apart from 0. As long as any integer a is not equal to 0, then 0 does not divide that integer a. Because if we take 0 and multiply it by any integer at all, k, we always produce 0. We can never produce a by multiplication. Now, when talking about integer divisibility, the term integer refers to all of the positive and negative integers and 0. So, in other words, we are considering integers in the set z, which we can write in list notation as follows. And so we can summarize this information. Suppose a and b are integers in the set z, then a divides b if we can find some integer k in z such that b equals k times a, i.e. integer a divides integer b if we can produce b by multiplying a by some integer k. And note once again that we define integer divisibility in terms of multiplication. And we read this notation, a bar b, as a divides b, and a crossed bar b as a does not divide b. And it's important to be aware that according to our definition, 0 divides 0. Sometimes you will see a different definition that is slightly different that prevents that from being true. So sometimes 0 divides 0 is excluded by definition. Now note that, say, 6 divided by 2 equals 3, and also 2 divides 6. It's fine to write both of those facts. Also, 18 divided by 9 equals 2, and we can write 9 divides 18. Both of those are fine. But if we say that 0 divides 0, which is true, we cannot write 0 divided by 0 equals 0. That is nonsensical. And so, whereas 6 divided by 2 equals 3 is equivalent to the statement 2 divides 6, and 18 divided by 9 equals 2 is equivalent to the statement 9 divides 18, 0 divides 0 is not equivalent to the meaningless statement 0 divided by 0 equals 0. You cannot write this down. It is false. And so if we start with the statement a divides b, we can deduce that b divided by a is an integer as long as a is not equal to 0. We'll now look at one of the most important concepts in divisibility, which is the idea of even and odd integers. An integer is even if it is divisible by 2. So 2 divides 18, since 9 times 2 equals 18, so we say that 18 is even. 2 divides 0, since 0 times 2 equals 0, so we say that 0 is even. 2 divides minus 14, because minus 7 times 2 equals minus 14, so minus 14 is even. And so we note that negative integers can be even. And so if A is an integer in the set Z, then 2 divides A is equivalent to saying that A is even. And the double-headed arrow symbol means is equivalent to. And so if A is even, it follows from the fact that 2 divides A that we can write A as 2 times k for some integer k in the set Z. So we can always write an even number in the form 2k, and this fact is important in proofs about even numbers. An integer is odd if it is not divisible by 2. So 17 is odd because 2 does not divide 17. How do we know that? Well, note that 17 is greater than 16, which is 8 times 2, and 17 is less than 18, which is 9 times 2. So there is no integer by which we can multiply 2 to produce 17. There is no integer in between 8 and 9. And for similar reasons, -5 is odd, i.e. 2 does not divide -5, and this example indicates that negative integers can be odd, just as they can be even. So for an integer a in the set Z, 2 does not divide a is equivalent to saying that a is odd. And if a is odd, we can always write a in the form 2k plus 1 for some integer k in Z, or in the form 2m minus 1 for some integer m in Z. So for example, we can write 17 as 2 times 8 plus 1, or as 2 times 9 minus 1. We can write -5 as -3 times 2 plus 1, or as -2 times 2 minus 1. Now, the fact that we can always write an odd number in the form 2k plus 1 or 2m minus 1 is important in proofs about odd numbers. And it's possible to prove that we can always write an odd number in one of these forms directly from the definition of divisibility, but the proof is slightly tricky, so I haven't done so. We'll now prove 3 facts about the addition of even and odd numbers. And to do so, we will use the definitions of even and odd numbers. The first fact that we will prove is that if we add an even number and an even number, then we produce an even number. So for example, 2 plus 6 equals 8. Even plus even equals even. Or 10 plus 24 equals 34. Even plus even equals even. We, of course, want to show that this holds for all even numbers, not just the specific numbers that we have used in those 2 examples. So what we do is to define 2 arbitrary even integers, which we will call p and q. So p, since it is even, can be written as 2 times a, where a is some integer. Q, since it is even, can be written as 2 times b, where b is some integer. And note that since we use different letters to define p and q, we define them in terms of integers a and b, they can represent 2 arbitrary and in general different integers. Note that if we had written p equals 2a and q equals 2a, then p and q would represent arbitrary but identical integers. We don't want that. So now we can add p and q, which becomes 2a plus 2b, and here follows the key point. We can factor out 2 to the front to produce 2 times a plus b, which we can write in the form 2 times c. And what is c? Well, c equals a plus b. But a plus b must be an integer. It must be in the set Z, because the sum of 2 integers is an integer. And so we have shown that the sum of two even integers can be written in the form 2 times c, where c is an integer, i.e. we have shown that the sum of an even integer plus an even integer is an even integer, as required. Secondly, we will show that if we add an odd number to an odd number, then we produce an even number. So, for example, 3 plus 5 equals 8, odd plus odd equals even, or 11 plus 13 equals 24, and again, odd plus odd equals even. So to prove this fact, we take R and S, which we define as arbitrary and potentially different odd integers, and we define them as follows. R equals 2d plus 1, where d is some integer, and S equals 2e plus 1, where e is some integer. And here we are relying on the fact that 2d plus 1 and 2e plus 1 follow the general form for an odd integer. And then we have, adding r and s, r plus s equals 2d plus 1 plus 2e plus 1, which becomes 2d plus 2e plus 2, adding the 1 and the 1, and then we can factor out 2 to leave 2 times d plus e plus 1, which we can write in the form 2 times f, where f equals d plus e plus 1, which itself, d plus e plus 1, must be an integer, because the sum of 3 integers is an integer. And so we have shown that the sum of two arbitrary odd numbers can be written in the form 2 times f, where f is an integer, i.e. we have shown that the sum of two odd numbers is an even number, as required. Finally, we prove fact 3. An even number plus an odd number gives an odd number. So, for example, we have 3 plus 4 equals 7, odd plus even equals odd, or 11 plus 12 equals 23, odd plus even equals odd. So, to prove this in general, we take u to be an arbitrary even integer and v to be an arbitrary odd integer. So, u is 2 times j, where j is an integer. V is 2 times k plus 1, where k is an integer. And then u plus v equals 2j plus 2k plus 1, which equals 2 into j plus k plus 1, factoring out the 2 from these two terms. And we can write that in the form 2l plus 1, where l equals j plus k, and j plus k must be an integer, since the sum of two integers is an integer. And so we have shown that an even number plus an odd number can be written in the form 2l plus 1, where l is an integer. So we have shown that an even number plus an odd number is an odd number, as required.